Uh, we have 10 minutes for the presentation, okay? So I will give you 2 minutes warning before the end. So let's start.
We are come from GT and Yeung College, and my name is Harry Chan, and his name is Jason and Michael and Wells. Okay, and our topic is about the probabilistic behavior of propagation of SARS with the generalized Fibonacci sequence. Okay, the background of SARS. SARS is a disaster happened in the 2003 in Hong Kong, and Hong Kong is the most serious place as the cases per citizen is the highest among the world. And we still don't know how the SARS is spread and also where it's come from. And our project is mainly focused on how the SARS is spread with our mathematical model. Okay, our method of study is use probabilistic instead of the epidemiology. And we introduce a generalized Fibonacci sequence, which is a Fibonacci sequence with we add 2 new parameters A and B into it. Okay, before we just talk about our model, let's have some definitions. First, N is to be like the nth day after the first case of SARS is found, and A is the probability of a person stay alive for another day, and B to be the probability per 2 days of an infected to infect another person, and Fn to be the probable cumulative cases of SARS on the nth day. Okay, and this diagram visualized our model, and as you can see on the 0 day, there's only 1 infector, and so that the probable cumulative cases is only 1. And to the first date, the probable as the person A, capital A, only have as little a chance to stay remain alive to the first day, so that the probable cumulative cases is only 1 times A. And to the second day, as first for the B, as there are little b chance of infecting another person, capital B, and also A has the chance of A as little a to stay alive for the second day, so that the probable cumulative cases is A squared plus B, and so on. Okay, we first try to find out the polynomial form of our Fn. So that we just write down the first 5 terms of our generalized Fibonacci sequence and observe it, and we just guess it. The form is shown on the bottom of this PowerPoint, and we will further prove it by the mathematical induction. And there is a very interesting term n minus ici in our polynomial form of our generalized Fibonacci sequence. As we made a table of it, and first for the order n, there's only 1, and order 1 and it generates 1, and order 2 it generates 1 and 1, and so on. And we discover an interesting fact that if we sum up all the numbers in the same order, we will obtain the Fibonacci sequence. So that maybe we can just call this the Fibonacci triangle instead of the New Pascal triangle. Okay, as the polynomial form of our generalized Fibonacci sequence is very difficult to find out the real number by substituting our A, B, and N. So that we use the matrix method to find out the generalized number of our generalized Fibonacci sequence. At first, we just make up a matrix Fn plus 2, Fn plus 1 equal to an operator AB10 times matrix Fn plus 1 Fn. And we define our F1 and F0 be A and 1. So that we can just represent Fn plus 2, Fn plus 1 into our operator AB10 to the power n plus 1 times the F1 Fo. We use the method of diagonalization of our matrix. We let A be AB10 and the transformation matrix be lambda 1, lambda 2, 1, 1. And after solve it, we discover that the lambda 1 is the term as shown in here, and lambda 2 will be the term shown in there. And we further let that matrix B, which is T minus T inverse AT. And after solving it, we discover it's very simple, and beauty can be represented by lambda 1 or lambda 2. As we want to represent our matrix A into a more simpler term, we just By this method, we just use the power of our use the power of n plus 1, and we found a n plus 1 equals to t b n plus 1 and t inverse, and we finally found fn plus 2 and fn plus 1 can be represented in the following term. Okay, here is our generalized Fibonacci sequence. As when we put a equals to 1 and b equals to 1, we found that is equal to the general term of the original Fibonacci sequence. Okay, now back to the case in SARS in 2003. Okay, we mainly focus on the Hong Kong cases, as this data is obtained from the WHO website. And we plot a graph in Excel, and we obtain this graph. Okay, and we divide this graph into 3 stages. As the first stage 1 is the first 60 days of the SARS disaster, and the number of cases increased very slowly, and we don't have enough data as WHO do not have any. And for stage 2 is our mainly focus on it, as it's the most serious time. Okay, and stage 3, the number of cases start increase slowly and become flat. And why we choose stage 2, as the Hong Kong people has no alertness at that period, and they don't have any special preventive measures in this stage. Okay, we try to find out A and B by analyzing Fn and the graph. And as we want Fn to be increasing during the period, we first assume the first term A plus square root A squared plus 4B over 2 larger or equal than 1. So that it can, that's one of the constraints to the Fn's to be increasing. And after solve the equation, we discover A plus B is larger or larger than 1. And for the second term, after the following steps, we got is smaller than 1, such that it will become very small when n become very large, such that we can write it in this form. And we use a logarithm of Fn to obtain a linear equation with variable n. And let's look in this equation is in the following term, and y-intercept is that term. Okay, we try to find out A and B by analyzing the following data. And we take the small n to be the day, large n to be the cases, and we use logarithm n to obtain the following graph. And by linear fitting, we find out the graph is as y equals to 0.1085x minus 0.2158. Comparing this this equation to our original linear equation obtained from the logarithm of our generalized Fibonacci sequence, we can get A equals to approximate 0.85 and B equals to 0.3. Okay, now back to the meaning of A and B. And we find out that under our model, the probability per day of an infected to remain alive and be infectious is about 0.85, which is mean 85%. And for the probability per 2 days for an infected to infectable normal person is about 0.3, which is same as 30%. And we discover a very interesting fact. If reaches a person stay for the probability for a person to remain alive for 30 days is the probability is about 1 over 1,000, which it has a slightly chance of stay such a long period under no medical treatment. Okay, this compare our model prediction and the case in HK, and we found that our model quite fit the case quite well in the first 2 periods. Okay, in conclusion, the probability under our model, the probability per day of an infected to remain alive and be infectious is about 85%, and probability per 2 days of an infected to infectable normal person is about 30%. And we believe that the generalized Fibonacci sequence gives a very good approach to predict the spread of the SARS case. And under our model, we believe that if we don't do any preventive measurement during the period, the case will be increased rapidly during the days. And our model maybe can be applied to other epidemiology by other viruses. by substituting different A and different B. Thank you.